Hello children, I hope you are all doing good. I welcome all of you for today's class. Today we are going to learn an interesting concept of numbers. In fact, we know that the area of a square is given by the product of its length of a side with itself. That is, the area of a square is nothing but side multiplied with side, which is side square. Let's try to see the various areas with the given sides. So, if you observe the table, if the side of a square is 1 centimeter, the area is 1 multiplied with 1, which is 1 centimeter square. So, similarly, if you observe the side with the 2 centimeter, the area will be 4 centimeter square. If you have side with 3 centimeter, we have area with 9 centimeter square. And so, in general, we can observe that if a side of a square is a centimeter, its area will be product of a with itself, that is nothing but a square, we can say. Students, if we observe all these numbers 1, 4, 9, 16, we can observe that all these numbers could be written as product of the same number. That is, if you observe 1, we can write it as 1 multiplied with 1. If you observe 4, we can write it as 2 multiplied with 2. If you observe 9, we can write it as 3 multiplied with 3. So, all these numbers such as 1, 4, 9, 16, 25 and so on, we call these numbers as the square numbers. In fact, we can also call it as the perfect squares. In general, if we have a natural number say m, if we can write this m as product of n with itself, that is, if we can write m is equal to n multiplied with n, that is equal to n square, then we say that this m is a square number. Remember, m is also a natural number here. In general, if a natural number m can be written as n multiplied with n, that is n square, where n is also a natural number, then we say that m is a square number. Students, let us check whether a number is a square number or not. Say for example, let us find whether 24 is a square number. Well, we all know that we can write 4 square, that is 4 multiplied with 4 is 16. And then what is the next square? We will go with the product of 5 with itself, that is 5 multiplied with 5 is equal to 25. So, we observed that 4 square is 16 and 5 square is 25. So, we can easily say that the 24 lies between 16 and 25. But do we have a number between 4 and 5 whose square is 24? It is not possible, because there is no integer present between 4 and 5. So, by this we can say that 24 is not a square number. Students, we have seen what are square numbers. Now, let us try to observe some of the properties related to these square numbers. Students, let us try to observe the squares of starting from 1 to 20. Observing the squares, let us try to identify some of the properties. Students, if you observe this table, we have a column containing all the numbers and the other column containing their squares. Look at the number 1. If the number is 1, its square is 1. If you have a number 2, its square is 2 multiplied with 2, which is 4. When the number is 3, its square is given by 3 multiplied with 3, which is 9. If you have a number 4, their square is 16. If the number is 5, multiplied 5 with 5, so we get 5 times 5, which is 25. Students, we can also try to proceed after 20. Say you take 21, multiply 21 with 21 and check what is its product. So, like this we can proceed to get all the squares of the given numbers. Now, when you observe all these squares of the given numbers, we can try to list out some of the properties. Say for example, you can just have a look at the table and observe that none of the digits in the units place will have 2, 3, 7 or 8. So, we can only see the numbers 0, 1, 4, 5, 6 or 9 at units place. So, if you observe all the square numbers, it actually ends with 0, 1, 4, 5, 6 or 9. That means, if you look at all the units place, only these numbers will be present. So, none of these numbers ends with 2, 3, 7 or 8 in its units place. So, this is the first property which we can say what numbers are possible in the units place and which are the digits which are not possible in the units place. So, if you observe the right column where we have the numbers such as 1, 9, 11, 19, 21. So, we observe that all these numbers have 1 or 9 in its units place, isn't it? Well, if you look at their squares which are on the left column, we see that all these squares have 1 in their units place. Look at there, we have square of 1 is 1, square of 9 is 81, square of 11 is 121. So, we see that whenever a number have 1 or 9 in its units place, its square number will end up with 1 in its units place. Well students, by now we have seen two properties. Now, observe another table and we will try to make an inference which will give us another property. If we observe this table, we have the table which are containing the squares and the numbers. If you observe the right column, we have the numbers such as 4, 6, 14, 16. From this we can make a note that all these numbers ends with either 4 or 6 in their units place. Now, proceed to their squares which are on the left column. The square of 4 is 16, the square of 6 is 36, the square of 14 is 196, the square of 16 is 256. We can see that whenever a square number ends with 6, then the number for which it is a square number will either have 4 or 6 in its units place. Students, by now we have seen three properties. Now, let us try to observe few more. Whenever a number ended with 1 0, how does its square number ends with? Let us find it out. Say for example, when we take a number 10, what is its square? Its square is 10 multiplied with 10, which is equal to 100. So, we observe that 10 have 0 in its units place, but observe 100, we ended up with 2 zeros. Both units place and tens place ended up with zeros. So, when we have 1 0 in its units place in the number, its square ended up with 2 zeros. Let us check one more example. Take a number 20. 20 ended up with 0 in its units place. Look at its square, which is 20 multiplied with 20, we get the product 400. And again it ended up with 0 in its units place, and in fact even in the tens place we see the 0. So, we had 1 0 in 20, but when you come to the square we had 400 where we ended up with 2 zeros. So, this is one property where we say that whenever a number have 1 0 in its units place, its square number will end up with 0 in its units place. In fact, it ended up with 2 zeros. Now, let us observe one more property. How about 5? When we have a number which is ended up with 5, how does its square number ends up with? Let us check it out. You take an example 5. What is the square of 5? 5 multiplied with 5, which is equal to 25. 25 ended up with 5 in its units place. Very good. How about another number? Let us take a bit bigger number. Take 25. 25 ended up with 5 in its units place. Well, let us find out its product. When you multiply 25 with 25, you can do it stepwise and you end up with an answer 625. The 625 is also having 5 in its units place. So, we can say that whenever a number ends with 5 in its units place, its square will always end up with 5 in its units place. So, by this we have seen the 5 properties of a square numbers. Students, let us revise all these 5 properties once. The first property we have observed that all the square numbers ends up with 0, 1, 4, 6 or 9 in its units place. We found that none of the square numbers ended up with 2, 3, 7 or 8, isn't it? Well, let us go to the property number 2. We have seen that whenever a square number ends up with 1, its number ended up with either 1 or 9 in its units place. The third property was whenever a square number had 6 in its units place, the number had either 4 or 6 in the units place. And then we have seen that the property 4 was whenever a number ended up with 0, its square number ended up with 2 zeros. And at the end, we found that whenever a number had 5 in its units place, the square number also ended up with 5 in its units place. So, by this we have seen all these 5 properties. Students, let us try to observe some of the very interesting patterns related to the square numbers. Firstly, we all know what are triangular numbers, isn't it? So, those numbers which can be arranged into triangles are called triangular numbers. Let us try to look at some of the examples. If you look at the given figures, we have numbers 1, 3, 6, 10. So, we could arrange all these numbers in terms of a triangle. So, these are some of the examples for the triangular numbers. Now, how does these triangular numbers are related to square numbers? Well, that is a pattern that we are going to find now. Whenever you take two consecutive triangular numbers and when you add them, try to observe what we will get. Suppose, which are the first two triangular numbers? We have 1 and 3. When you add these two triangular numbers, 1 plus 3 is equal to 4. But we know that 4 is nothing but 2 square. 4 is a square number. Let us try to observe the next two consecutive triangular numbers. We have the numbers 3 and 6. When we add these two, 3 plus 6 is equal to 9, which is again nothing but 3 square, a square number. So, like this, whenever you take two consecutive triangular numbers and when you add them, we always end up with a square number. So, that is the first pattern we can observe, adding up of a triangular numbers. So, a sum of two consecutive triangular numbers will give us a square number. Well, now let us try to go on to the next pattern, but this time let us try to observe the numbers which are present between the squares of two consecutive numbers. Students, let us try to observe the squares of the consecutive numbers. Look at that. So, we see in the figure that 1, which is nothing but 1 square. After 1, we have the numbers 2, 3 and 4, but we know that 4 is nothing but 2 square. And then after 4 we have 5, 6, 7, 8 and then comes 9, which is our 3 square. So, similarly you proceed on, we get 10, 11, 12, 13, 14, 15, then comes the next square number which is 16, which is nothing but 4 square. Now, let us try to observe the numbers present between two consecutive square numbers. Our first square number was 1 and the second square number was 4. What are the numbers present between these two? Yes, they are 2 and 3. So, we can say that between 1 square and 2 square, that means between 1 and 4 there are two non-square numbers. But remember, we can write this 2 as 2 square minus 1 square and this subtracted with 1, because 2 square is 4, 1 square is 1. So, 4 minus 1 is 3 and then 3 minus 1 is equal to 2. So, we can write 2 is equal to 2 square minus 1 square minus 1. Now, let us try to take the next two consecutive square numbers, which are they 4 and 9. And between these two square numbers, observe how many other non-square numbers are there. We have 5, 6, 7, 8. Totally, we have 4 non-square numbers. And then observe here, we can write 4 as 3 square minus 2 square, that is 9 minus 4, we get 5, minus 1 is equal to 4. So, we can write this 4 as 3 square minus 2 square minus 1. Remember the pattern that we are writing. Whenever we have a square number, say 4, we are reducing it by 1 and taking the squares of that number and then a number less than that. Let us try to observe one more example. The next consecutive square numbers are 9 and 16, that is nothing but 3 square and 4 square. Between 3 square and 4 square, we have these non-square numbers 10, 11, 12, 13, 14, 15, which are totally 6 in number, and we can write this 6 as 4 square minus 3 square minus 1. So, like this you can try to observe that whenever you take a numbers which are present between two square numbers, we can always try to represent it in the following way. Say for example, when you take two square numbers such as n square and n plus 1 whole square, there are totally n plus 1 whole square minus n square minus 1 elements. So, if we try to simplify this, we get n square plus 2n plus 1, because n plus 1 whole square is nothing but n square plus 2n plus 1, and we are left out with minus n square and minus 1. So, we can cancel n square and minus n square, we can cancel 1 and minus 1. So, we are left out with 2n there. Students, we had observed that whenever we have the squares of two consecutive numbers, that is whenever we have n square and n plus 1 whole square, in between these numbers we have 2n non-square numbers. So, let us try to have an example. Can you find how many non-square numbers are present between 100 square and 101 square? Well, let us take 100 as n, and then n plus 1 is 100 plus 1, which is 101. So, we have these two consecutive square numbers 100 square and 101 square. What was our n? Our n is 100. Whenever we have two consecutive square numbers, that means whenever we have n square and n plus 1 whole square, in between these two we find 2n non-perfect squares. So, therefore, between 100 and 101 square there will be 2 times n. Our n is 100. So, 2 times 100, which is equal to 200 non-square numbers. So, we find that there are 200 non-square numbers present between 100 square and 101 square. Students, by now we had seen two patterns. Now, we are going to see a very important pattern which will be very much helpful even in our higher classes. Let us try to see the sum of the first odd natural numbers. Have a look at that. Students, we know that the first odd natural number is 1. So, we can write 1 as 1 square. Let us try to observe the sum of first two odd numbers, that is 1 plus 3, which is equal to 4, that is nothing but 2 square. Now, try to observe the sum of first three odd numbers, that is 1 plus 3 plus 5, which is equal to 9, but we know that 9 is nothing but 3 square. So, similarly, when you try to observe the sum of first 4 odd numbers, we get 16, which is nothing but 4 square. So, if you observe, whenever we have the sum of first n odd numbers, we have n square as its sum. So, this is one property which we can see, that the sum of first n odd natural numbers is always n square. Students, in fact, if a number cannot be expressed as a sum of successive odd natural numbers from 1, then it is not a perfect square. So, this is one way where we can make use to identify whether a given number is a square number or not a square number. To check whether 25 is a square number, you start subtracting the starting odd natural numbers starting from 1. Say for example, here we have 25. So, we are going to subtract the first odd natural number 1. So, 25 minus 1, we got 24. So, from this number subtract the next odd natural number, which is 3. So, 24 minus 3, we get 21. So, when you start subtracting all the odd natural numbers from the obtained answer, at the end we got that 9 minus 9 is equal to 0. Since we had subtracted all these numbers and we ended up with 0, we can write this 25 as 1 plus 3 plus 5 plus 7 plus 9. So, this means that 25 can be expressed as a sum of consecutive odd numbers starting with 1. So, therefore, by our property we can say that 25 is a perfect square. Students, we saw that we can write 25 as 1 plus 3 plus 5 plus 7 plus 9. See here, you can see that there are 5 numbers. So, therefore, we can write this 25 as 5 square. Let us try to check another number. Let us take 38. Now, from this 38, let us start subtracting the odd numbers from 1. So, when you subtract 1 from 38, we get 37, then subtract 3, we get 34, subtract 5, we get 29, and so on. At the end, when you subtract 11, you end up with 2, and when you subtract 13 from 2, we get minus 11. So, we got a negative number. So, here we can't express 38 as a sum of consecutive odd numbers starting with 1. So, therefore, we can say that 38 is not a square number. Students, now let us try to observe another interesting pattern based on the squares of odd integers. So, now observe some of the squares of odd integers. Firstly, we know that 3 square is equal to 9, which can be written as 4 plus 5. Here, let us try to write 4 and 5 in terms of 3 square. So, here 4 is equal to 3 square minus 1 by 2 and 5 is equal to 3 square plus 1 by 2. Now, let us observe 5 square. 5 square is equal to 25, which could be written as 12 plus 13. Here 12 can be written as 5 square minus 1 by 2 and 13 is equal to 5 square plus 1 by 2. In a similar way, even observe 7 square, which is equal to 49, and this can be written as 24 plus 25. Even here we can write 24 and 25 in terms of 7 square as 24 is equal to 7 square minus 1 by 2 and 25 is equal to 7 square plus 1 by 2. Let us also observe 9 square, which is equal to 81, and this can be written as sum of 40 and 41. Here 40 is equal to 9 square minus 1 by 2 and 41 is equal to 9 square plus 1 by 2. So, in general, if m is an odd integer, then we can write m square is equal to s plus 1, where s is equal to m square minus 1 by 2 and s plus 1 is equal to m square plus 1 by 2. We can observe that the square of any odd integer is equal to sum of two consecutive positive integers. Well students, now let us try to observe a final pattern based on the product of two consecutive odd integers or consecutive even integers. Students, observe the following products and let us try to find the pattern based on them. Observe the product of 11 and 13. So, 11 times 13 is equal to 143, which we can write it as 12 square minus 1. Since we can write 11 is equal to 12 minus 1 and 13 is equal to 12 plus 1, we get 11 times 13 is equal to 12 minus 1 times 12 plus 1, which is equal to, here we can use the formula a minus b times a plus b, which is equal to a square minus b square. So, we get 12 square minus 1. Similarly, we also have 13 times 15 is equal to, 13 can be written as 14 minus 1 times 15 can be written as 14 plus 1. So, again by using the same identity, we get 14 square minus 1. Let us also observe another example, 29 times 31, which is equal to 30 minus 1 times 30 plus 1, which is equal to 30 square minus 1. So, these are the product of two consecutive odd natural numbers. Let us observe a product of two consecutive even natural numbers. So, for example, 44 times 46 is equal to 45 minus 1 times 45 plus 1, which is equal to 45 square minus 1. Students, in general, whenever we have the product a plus 1 times a minus 1, that will be always equal to a square minus 1. Observe, here both a plus 1 and a minus 1 will either be odd integers or will be either even integers, because the difference between these two numbers is 2. Students, Finally, we will observe one of a very interesting pattern. 1 square is equal to 1. So, 11 square is equal to 121. Then 111 square is equal to 1331. So, we are writing the digits in such a way the numbers have been placed as shown here. And finally, we will also take another square which is 1111 square, that is equal to 14,641, where the digits have been written as 14641. And in a similar way, we can proceed further for the squares of the numbers having the digits only 1. Here we observe that each number except the end numbers in a row will be obtained by taking sum of two immediate above elements of preceding row. We call the numbers so obtained in the shape of a triangle as Pascal's triangle. Students, thus we found various patterns related to square numbers. So, here we end the class. Before we wind up, let's try to recollect what all things we had learned today. We started our class with the definition of square number and then moved on to the properties of square numbers. We have also learned various patterns related to square numbers. But wait, we need to answer a question, that is, how do we find a square of a given number? Well, we will answer this question in our next class. Hope you had enjoyed the class. Have a good day. Thank you.